All right. So you all saw that I sent you an exam, correct? And I hope you're working on it and that you're finished with it as soon as you can. Because we need to prepare for exam 3. It's going to be on Friday. We have very little time. Actually, painfully little time for this. And I'm not even sure if I'll be able to say everything I want to say about integration before the 3rd exam. So first of all, here is where we left last time. So remember that we figured out how to find the closed sum for the sum from 1 plus 2 plus 3 all the way to n. We saw that the closed form of the sum is n times n plus 1 over 2. Right? There are also similar formulas, which I'm not sure. I'll try to go over it if we have a little time. There is a formula for k squared. I will not make you remember this. This is very easy. This you should be able to derive on your own. I showed you how to derive this. Derivation for the k square formula and for the k cube formulas are actually a little harder. You use an algebraic trick. But if I utilize those formulas, I will give them to you in this form. So the central problem of integral calculus is as follows. If we have a curve, y equals f of x, and this curve is stretched between x equal to a and x equal to b, how do we find the area between this curve and the x-axis? Now, it has enormously many applications. For example, if you think about this function as a force and this as distance, distance times force represents work. So the area between this curve and the x-axis will represent total work done on a moving particle, right? And work is a physical property, work energy theorem, for example, right? Is a statement, in fact, about areas of curves. So geometrically, how do we do this? So let's look at a very basic example. So suppose that we have that y equals f of x, which is just equal to x. And we look at this x between 0 and 1. So x is between 0 and 1. Let's draw a picture of it. So this is y equals x, is just this line. This here is 0. And this here is 1. What's the area between this curve and the x-axis? Can you see it? Well, this area is the area of a right triangle. What's the height of the right triangle? The height is 1. So the area is equal to 1/2 base. What's the base? Base is just 1 times 1. So in fact, area is just 1/2. We just figured this problem using only geometry. But if I select a curve that is slightly more difficult, any curve that's slightly more difficult, as in y equals f of x, which is x squared. Let's say again x is between 0 and 1. Now the shape is that of a triangle whose hypotenuse is bent. So it's no longer obvious what it is. Now what's the idea of calculus? The idea is that what we do is we take any sort of problem and we approximate this problem with the appropriate pixels for it. So for example, if I look at a curve, the simplest curve is a line. So I take any curve and I approximate it by line segments. The line segments are the pixels for the problem. Now for the case of area, what do you think might be the pixel? What is the simplest object for which area is easy to calculate? Or rectangle, right? Square is very particular, yes, but then rectangle. So what we do is we digitize the shape. And I put it in quotation mark. This is a vague term. Digitize f of x equal to x squared. And by that I mean do the following. So here is the curve y equals x squared. This is 1. This is 0. So what we do is we are first going to approximate this shape by two rectangles. So let's say that we approximate area is, let's approximate it what we call R sub 2. So approximate area with two rectangles. So what we do with that is we take the base and subdivide it into two equal intervals. So this point here is 1/2, correct? And then what we do, this is using right-hand approximation, at the point 1/2, we erect the first rectangle. And at the point 1, we erect second rectangle. Now this, of course, does not look like a very good approximation, but it's a start, right? So instead of looking at this curve, we think of the area as the sum of the two rectangles. What are the areas of those two rectangles? R2. The areas is, well, the height of the first rectangle at 1/2 is f of 1/2 times the width times 1/2 plus f of 1 times 1/2. Okay? So that is simply (1/2) squared times 1/2 plus 1 squared times 1/2. Correct? Now there is no need to calculate the sum. What can you say about it? Is the sum going to be more than what appears to be the area below the curve, or less, or equal to it? Well, look at the yellow rectangles. They are completely encapsulating within them the area below this white region. We're interested in this region. Correct? So this is more than the actual area. More than the area. Now what we can do then is, let's, instead of using R sub 2, let's use R sub 4, approximate by 4 rectangles. Now what's R sub 4? So what it means is that I take this width from 0 to 1, and I subdivide it into 4 equal subintervals. So that means that here I have the point 1/4. Here I have the point 3/4, correct? Now over the point 1/4 I erect this rectangle. Then over the point 1/2, between 1/4 and 1/2, I erect this rectangle. So we have this rectangle, we have that rectangle, we have that rectangle, and here is another one. Now notice what happened here. The digitization is better, right? We have 4 approximations. The widths of those rectangles has shrunk. And what happened is that those rectangles are better fitting the actual curve. So it stands to reason that if we continue this process, if we now, if this is R4, so let's just see what R4 is. R4 is, notice how this works. So this goes f of 1/4, and we're trying to write a pattern, right? F of 1/4 times 1/4 plus f. You can put 1/2, but nicer to see that, notice, this is the second rectangle. So this is f of 2/4 for the second rectangle, right? So first rectangle corresponds to 1/4. Second rectangle corresponds to 2/4. What is going to be the third rectangle? F of 3/4 times 1/4 plus f of 4/4 times 1/4. Okay, that's R4. Now notice it becomes very unwieldy to write the many terms, right? So here is first term, second term, third term, fourth term. So we begin to utilize Riemann sum. So what is that? This is summation where k starts from 1 and ends where? So k stands for how many rectangles we are summing. How many rectangles? What's the last term here? 4. In general, n, right? We are going to modify it in a moment. But in this case, for r sub 4, this is going to be 4. And here we have the function f, which is x squared, but that's in a moment. F of what? What changes here? So the 4 is always the same in every term we are adding. So what is here? Here is our k. So it's f k over 4 times 1/4. Okay? So it takes this form. Now this is, I just drew R2, I drew R4. It becomes a little more difficult as I go along to draw more of those rectangles. But can you see what's happening in general? So can anybody here write me what should be Rn, an approximation by n rectangles? Because you see, the area, this is, as you can see, still not equal to the area. It's bigger than the area, but you can have this relationship. You have this relationship that R2 is, in this case, bigger than R4, and yet R4 is, just by looking at geometric picture, is bigger than the area that we are trying to find. So how do I write R sub n? Approximation by n rectangles. So that is the sum of how many areas? N areas. So it's the summation from k equal to 1 all the way to n what? What's the area of a particular rectangle? So first of all, if we approximate by n rectangles, what's the width of each rectangle? We take it, we divide it in exactly the same amount, so it's going to be 1 over n. And here we have f of what? Do you see? Yes, k over n times 1 over n. So what we are getting is, what does f do to this region? So it's k equal to 1 to the power, to n. And what f does to any input, it squares it. So it's just k over n squared times 1 over n. Right? I'm going to explain this again using the general example, and yet we'll do it several times, and hopefully you see why we have this k over n squared times 1 over n. So now let's see what the sum is like, so we can write it a little better. So the first term is 1 over n squared times 1 over n. The next term is 2 over n squared times 1 over n, and so on, right? Until we get to n over n squared times 1 over n. So what is this? Notice what I can factor from each term here. So this has 1 over n squared times 1 over n. This one has 1 over n squared times 1 over n. So what I can do is I can write this as 1 squared times 1 over n cubed plus 2 squared times 1 over n cubed plus n squared, this number squared, times 1 over n cubed. You see what I did? Each of those terms has a denominator which is n squared in fact. So we have 1 over n cubed, 1 over n cubed, 1 over n cubed, and when I factor this out, what do I observe? I observe that I have in parentheses 1 squared plus 2 squared plus 3 squared plus n squared times 1 over n cubed. Okay? And now this is the sum that we already have a closed form for. So this sum can be simplified and written as n plus 1 times 2n plus 1 divided by 6 times 1 over n cubed. So I wrote r sub n in this closed form. I found a formula for it. So then area that I'm searching for is simply limit as n goes to infinity. Because as I increase the number of rectangles that are approximating this curve, and their width is getting smaller, the area is more precisely approximated. So in the limit, I believe that the area will be perfectly approximated. So this would be limit as n goes to infinity of n plus 1, 2n plus 1 over 6n cubed. Can you tell me what's this limit? Now this is something we learned a long time ago, a while ago at the beginning of the semester. And this is very easy since this is a numerator is a polynomial, denominator is a polynomial. It's very easy to see what should be the limit as n goes to infinity. This rational function is determined by only the leading coefficients, which are what? So what is this? What's the leading coefficient on the top? Well, with the coefficient. So it's n to which power? Numerator, 1, 2, 3. In fact, if you multiply it out, the leading term is n cubed. Now, n times 2n, this is the same as 2n cubed. Everything else will not matter. Divided by 6n cubed. And what you get is 1/3. You get 1/3. All right? So here is the idea in general. In general, if y is equal to f of x, and where x is between a and b, we have this situation. So we want to so we want to partition this into many small rectangles. So here it is, right? So here is the right-hand method. So we take this, we divide it into n rectangles. Here we use the right-hand point. So here is rectangle 1. That's A1. Here is rectangle A2. Rectangle A3. And so on and so forth until we arrive at the last rectangle. A sub n. You see what we're doing? We're taking this curve and we imagine that we stick underneath this curve many very thin rectangles. Now this curve is y equals f of x. Now if I take Rn, the approximation by n rectangles here for this function, this is going to be the summation of the areas A1 plus A2 plus A3 plus A sub n. So what I need to do is I need to figure out an expression for the kth rectangle. So this is just the summation of A sub k, where k goes from 1 to n. Now, let's just blow this picture up and see what A sub k looks like. So we have So here is a segment of this curve that I blew up. A second, let me draw it better. So here is sum a sub k. Just zooming in on one of those rectangles, sum a sub k. Its area consists of delta x and of the elevation h sub k, the height at the cave place. So first of all, tell me what is delta x. Can you see what it is? We placed underneath this curve, so this curve stretches from over the interval from a to b, and we have n approximating rectangles, and each rectangle has the same width. What's delta x? Right, so what you do is you take the full length of the interval and divide it into n segments. So that would be b minus a divided by n. Everybody says it? Now, h sub k, so since we're using the right-hand approximation, h sub k is always using the right-hand point on the x-axis to plug into the interval. So we're using this point here. This point is x sub k. So we can say that h sub k is equal, so the height is created by taking the right-hand point of the interval and plugging it into the function, and that gives us the altitude. Okay? So the altitude will be simply f of x sub k. Now what is x sub k? How do I find it in terms of the interval, in terms of the points a and b? Let's see how we find it. So if this point is a, then if I move here, that is x1, right? If I move here, that's x1. If I move here, that would be x2. And next is x3, so on and so forth. What can you see is x1? So x1 is the point A plus, we move one displacement, plus 1 times delta x. Do you see that? So that's equal to a plus v minus a over n. What is x sub 2? And again, I want a simple formula in terms of the index, right? So how do I get to x sub 2? So x sub 2 corresponds to, you see what we do here. So when we are using the right-hand approximation, we are taking this interval and we pick, we always pick the right-hand point of the interval to plug into the altitude, to plug into the function to create the height of the rectangle. Make sense? This is very important. You all have to follow me. This is the, I suppose, setting up integrals is one of the hardest topics in, for the third exam for this region. So how do I get x sub 2? A plus, so I begin with a. How much do I need to displace to get to x sub 2? 2. Yes, you see, 1 delta x, 2 delta x. So you can always begin with a and displace two widths of a rectangle. You see what you do, right? So this point is obtained by displacing from a 1 width of a rectangle. x2 is obtained by displacing from A two widths of a rectangle. So what we get is A plus 2 B minus A over n. What's x sub 3? You can already guess.
A plus 3 delta x.
So that's a displacement of 3 units. That's A plus 3 B minus A over n. Okay? So therefore, h of k, which is equal to f of x sub k, it's equal to f applied to A plus k times B minus A divided by n. So area between y equals f of x and x axis over interval AB is approximately equal to summation k equal 1 to n of the area of the approximating rectangles, which is, as we just saw, this is k equal 1 to n of the function f a plus k b minus a over n times b minus a divided by n. This is representing the height of the rectangle. And this is width. And the area is equal to, we would say, area is equal to the limit as the number of rectangles goes to infinity, so that the rectangles get more and more thin, and you get more and more of them. Can you picture this? Can you see what's happening? So this is like saying, notice that the sum is approximately the same as sum f of x k delta x. And in the limit, there is a notation that we write that reminds us of what we're doing. This is sum. So when you take the limit, this sigma, you write it as an s, right? So the sum is over the interval from a to b, and it's of f of x times little dx. Little dx means very little width, and this means height of rectangles, right? So this means take the function and sum over the many heights and widths of the curve. Okay, so let's look at examples. You understand this notation? It's supposed to remind you of what you need to do to compute it. This means sum a lot of very thin rectangles whose height is f of x. So example, calculate the integral from 0 to 2 of 3x dx. Let's begin with some simple examples. We're going to learn shortcuts or better ways of figuring this out, but there will be definitely a question where when you need to see that, where you're tested, that you understand this Riemann sum and you're able to do it by definition. You should be ready with this by the end of this weekend. There's not a lot of time. Solution. So first of all, what is this? So what we have is, we write that this integral this is limit as n goes to infinity of r sub n which is limit as n goes to infinity of the summation of n rectangles. K starts from 1 all the way to n of f of a plus k times b minus a over n times b minus a over n So first of all, we'll write f. What's a in this case? 0. Plus k times what? What's b minus a? 2 minus 0 over n. And 2 minus 0 over n. Now, this b minus a over n refers to what? So this refers to area. B minus a over n refers to what? The width, right? You have to not to forget what this O is, right? If you remember, then you don't need to just memorize this formula. So b minus a over n represents the width of this very thin rectangle. And this represents its height in the cave place, right?
And n would be 2 here?
No, n is approaching infinity. N is the number of rectangles that approximate this curve. Right? So it's always going to be to approach infinity. Remember this picture. You are taking this curve and you digitize it. You stick many, many very thin rectangles underneath. The more, the better.
It's so. Okay.
Right. So what we have here, limit. This, guys, you have to practice. This I am terrified what I'm going to see on the exam. Right? I just complete misunderstanding. This is limit as n goes to infinity. We're going to practice a few setups and also evaluation. So k equal 1 to n. What's f? What is f doing to the input? The function, what is the function here? 3x. That means what? That means the function does what? What does the function do to the input? Wonderful. I couldn't have said it better. It multiplies the input by 3. The input looks like 0 plus k times 2 over n. Right? So what you have here instead of f, 0, by the way, you don't need to write. So this would be just 3 times, I'll put it in parentheses just for safety, k times 2 over n times 2 over n. You see what I did? So what can I do here? You see that we have 2 over n, 2 over n. I can factor it out. So what I have is and I can factor 2 over n, so I'll factor it out here, 2 over n squared times k. Do you see that 3 times 2 over n squared? It's not dependent on k. So this is just the same number multiplying each k. So 1 is multiplied by this number, 2 is multiplied by this number, 3 is multiplied by this number. Just to be safe, let me write it out. Sometimes write the sum out so that you get very comfortable with it. What is this? If I put it in parentheses, this is 3 times 2 over n squared times 1 plus 3 2 over n squared times 2 and so on. 3 2 over n squared times n. So you can see that each term in the sum has 3 times 2 over n squared as a factor. So I can write this as limit of 3 2 over n squared 1 plus 2 plus n. And notice again we see a sum, one of those sums on the board. This sum, in fact, you are supposed to know how to establish on your own. I did show you how to do that. So that is limit as n goes to infinity of 3 2 over n squared. The sum is just simply n plus 1 divided by 2. Can you see what this limit is going to be now? What is the limit equal to? Just 6, very good. So this 2 squared cancels with this. So we have 3 times 2, and then everything else is just eliminated, right? So this is, let me possibly write it. Maybe some of you have questions that you just don't want to ask me. So this is like 3. And here we have the 2 squared is 4 times n times n plus 1 over 2 times this n squared. And this is the same as the limit of 3 and then 4n squared divided by 2n squared, which is the same thing as simply the n squares cross out. 4 over 2 is 2 times 3 is 6. Okay. That's the area, precisely. So again, you understand the idea of how we found this area. We basically had this curve, and underneath it, we stuck a lot of rectangles. Actually, this area could have been obtained very easily because this is a straight line, and therefore the area is that of a right triangle. So we did not have to use this procedure. You could have tested using a simple geometric procedure what the area should have been. Example. Set up, but don't evaluate the integral. All right. So first of all, and again, when you do those procedures, try to think why the formula comes out, okay? So try to come up with the formula, don't look at anything. So solution, first of all, what we have is, what's delta x? Or we partition into n rectangles, right? N segments. That makes delta x equal to what? Yes, so it's equal to 5 minus 3 over n, which is 2 over n. Now, what does delta x represent? The width of a thin rectangle. Somewhere, every rectangle that we're using is having the same width, which will be 2 over n. Okay? So delta x is 2 over n. Next, we want to find, so the area is something of the form, area is approximately f of x1 times delta x, which is area of a first rectangle. That's a sub 1. plus f of x2 times delta x, which is a sub 2, and so on and so forth until we get to f of xn delta x, which is the last rectangle. All makes sense? Up to here, it makes sense what we do, right? Now, how do I obtain x1? So I can just draw myself a picture. So how am I going to construct those rectangles? So the idea is I'm going to go like this. So this point is what? A. Okay? This point is A. This point is x1. This is x2. This is x3, x4, and so on and so forth. And when we approximate by rectangles, we decided that we're going to pick the right hand point as the thing that we put into the function. So we take this point, and we feed it into the function to create the height. So the height is f of x1. The height is at the rightmost point of each interval. And we decided that we are moving this way. Okay? So what is, let's just do right away what is x sub k? How do I obtain x sub k? That means x sub k is the point that is going to be used to find the height for the kth rectangle. What's x sub k? If I do this motion this way.
Is it x1?
Well, let's begin with x1 then. All right. So what's x1? Exactly, right? So I need it in terms of, because x1s are going to be changing, right? x2 are going to be changing depending how many rectangles we have here. So they change with n. So x1 is a plus 1 delta x. You see? A and 1 displacement, which is a plus, which is a plus 2 over n. What's x2? This is a plus 2 delta x, which is a plus 2 times 2 over n. And in general, x sub k is a plus k delta x, which is a plus k times 2 over n. Okay? Make sense? So what's f of x sub k? F of x sub k, what will it do to the input? It will write the input plus root of the input squared plus 1. Correct? So that will be, what is x sub k? That would be a plus k 2 over n plus root a plus k 2 over n squared plus 1. So therefore, the integral from 3 to 5 of x plus root x squared plus 1 this is limit as n goes to infinity of summation k equal 1 to n. And then what I have here is a plus k, well, not a, which is what was a? A I should have written as what? What's a here? A is the number 3. Plus k 2 over n plus 3 plus k 2 over n squared plus 1 underneath the square root. Very ugly expression, right? But the point is for you to be able to set the integral up. That's it. What you should be training yourself is to do the following. Looking at this Riemann sum, be able to re-express it as an integral, and vice versa. Yes?
So you wouldn't be able to use the a plus k b minus a over n?
Yes, you can. You don't have to do so much work if you understand it, right? Again, my hope is that in this very short hour, you get a sense of how to figure out this formula if you forget it, and many of you will forget it. Let's actually see if you can derive your own formula. So you see, I had the right-hand rule this way. Notice I decided to write the sum from left to right. Okay, so I'm going to give you a task to write it from in the opposite direction, from right to left. Example, set up integral from a to b of f of x dx. So let's just keep it abstract. From right to left. So what I mean by that is, if I look at this point here is b, right? So I displace. I want this to be x1. I want and all the way until you get to A. And here is how you move. So what you do is, your first point that you select is this. Then you move and select this. Then you move, select this. Okay. So let's see what we have. So what we do is we write limit as n goes to infinity summation where do I start k from and where do I end k? Well, k is an integer. So I want to start at b, I want to command it by k. How do I do that? So that should be f of x sub k delta x, correct? The first point, though, is not x1. The first point is b. So that would be x sub what?
0.
0. All the way to? If it's n, it's too many.
A.
Yeah, well, all a, but a is a number. So how do you get to a?
X sub n.
How do you get to x sub n? Here you go. You see, what happens in your mind then is you might see where you have to get, but you don't see how to control it by integers. K represents always an integer. A and b could be any numbers. They don't have to be integers.
K is 0 because
I could have set k equal to another number. It doesn't have to be 0. Depends on b minus a will be the full length here.
Is that what we have?
All right, let's do it slower. But this is what I'm talking about. That's what you need to practice. So first rectangle is at b. So where do I start? So I start with x sub 0. X sub 0 is b. Okay. My next is x1. How do I get to x1 if I want to start from b? x1 is easiest to find if I start at b. How do I get to x1? So it is
B minus x1.
no, that will be so b minus what?
Or delta x.
Delta x. B minus delta x. Yes, very good. So it's b minus delta x. What's delta x, by the way? Let's write that. That is b minus what? What's delta x? B minus a over n gives us, so b minus a gives me this length, divide by n gives me this segment. Okay? Now next is x2. What's x2? How do I get there? B minus 2 delta x. Right, and in general, x sub k is b minus k times delta x, which is b minus k b minus a over n. So you saw, I mean, when you do it slowly, right, and when I ask you those questions, you are able to get to the right answer. But you see what can happen if you don't practice this on the exam. You will just get confused. Like B, A, C. You will just not be able to put this Riemann sum together. So the Riemann sum is, or the area. So this integral from A to B of f of x dx can be also written as limit where n goes to infinity of the sum k equals 0, say, all the way to n minus 1. So now I have k rectangles. You see, from 0 to n minus 1, it's exactly n rectangles. And then I have f of b minus k b minus a over n times b minus a over n. So this is another representation of the rectangle, but now starting from b. Okay. Yes?
Where did you get the n minus 1 from?
The n minus 1 is, notice that I have, I'm using the right hand approximation. So this is the first rectangle. So I use this x0. x1 corresponds to already the second rectangle. x2 corresponds to the third. So the n minus 1th term will correspond to the height of the nth rectangle. Okay? Let's see. Now, in this case, what you have to do is you have to figure out what was the integral. So in other words, looking at the sum, you have to see how somebody was constructing this integral. Right?
Like what was the a to b?
What was the a to b and what was the function that was integrated? Now it might be very far from your concerns, but really, again, when you see any applications, you first put this formula into a Riemann sum, and then you figure out how to use shortcuts. So usually you have no application of calculus at the beginning. You put it, you approximate the problem by a Riemann sum, for example, and then you are able to use shortcuts. Ready? So what can you say were the a and b? It appears. Sorry?
5 and 7.
Wonderful, you see that. So notice that we began here at 5. It looks like we're displacing from 5. And we displace by segments of width 2 over n. Right? So we begin and we see that this is 5. You can figure out this 5. There is a very easy trick. Plug k equals 0. K equals 0 gives you 5. Now plug k equals to n. Right? That means displace from 5 as far as possible. That's by n segments. So that would be 5 plus 2 times n divided by n, which is 5 plus 2, and that gives you 7. That's good to hear that you see that it's 7. What function?
X to the 10th power.
x to the 10th power. So you understand how I was able to notice this. I see that this is 5, and this is 5 plus 2 over n and onwards, right? How far can I get this way? The very last point is 5 plus n times 2 over n. And you see that the farthest I can get is 5 plus 2. Gives me 7. You understand? Now this is the function is that it to the power 10. There is another solution which is also correct, is the integral from 0 to 2 of 5 plus x to the power 10. It's also correct. Okay, there is no, but they give the same answer. Okay, 5 plus x to the power 10 would also have been a correct answer. All right, what about B?
0 to pi over 4.
That's very good. 0 to pi over 4. Zero to pi over 4. Why from 0? Notice that if k is equal to 0, you see tangent of 0. And then if k is equal to n, that's the farthest you can displace from 0, you get pi over 4. What are we integrating? Tan x. Tan x dx. Good? So this you have to practice and practice and practice. There would be definitely a question about setting up integrals and a question where you have to evaluate integrals using the Riemann sum, using this long-winded, annoying procedure.
Third exam, May 18th, not 19th, right?
No, we have 19th, Friday. Friday is the last day of class, correct? So yeah, because what we have is we will have lesson on Thursday, and then the next day after that we have the third exam. That's the unfortunate thing about it. We have 3 more lectures.
So the final is on the 19th.
No, the final is on the 25th, if I'm not wrong.
25th. Oh, okay.
So 19th is third, 25th is final. I will try to possibly arrange so that you have a review if you want, right? So you might come and have a review for the final. For the third exam, only in office hours you can ask me regarding that.
Well, what time after? I'm sorry, 25th?
25th. Usual 6 to 8, yes. Finals worth 2 exams, right? You have a good shot at exam 2, I think, and if you again care, you have a shot for exam 3. If you understand, this is the hardest thing, I think. This is very hard, I think, especially on the first time when you deal with it, and if you have some algebra baggage. And it's of course bothering me terribly that I'm not telling you how this is very useful, but open any physics book. You see that this is one of the few things that you apply from Calc 1 all the time, right? So that you have a problem, you set it up as a Riemann sum, and then you have an integral.
Exam 2 is going to be when? I know you're said you're sending them home or whatever, but when would that be?
Exam what?
2.
I think I sent an email about it, right? I sent the exam 2 is in your. I sent you an email with exam 2 with a link to it, correct?
Yes.
So it's a take home. And I told you when it's due. I thought, when did I say? I said, I think this Tuesday, right? Yeah, so you have this week plus the weekend and Tuesday. And the exam is designed for 2 hours. So you should not really, I mean, I'm hoping you don't need to spend too much time on it. All right. All right. Let's practice a few more questions. So evaluate the integral from 0 to 3 of 4 plus 2x dx.
If it doesn't say otherwise, we assume it's left to right.
Sorry?
If it doesn't say otherwise, we assume it's left to right.
You can use right hand. I'm going to explain what's, I mean, left hand is just really the same, but you just pick the left hand point.
Okay.
All right. You can use whichever you want. I prefer the right hand point. All right. So first we can very quickly set it up. What is delta x?
3 over n.
3 over n. Very good. Then I need to figure out what is x sub k. X sub k is the kth approximating point. What's that? Right. Well, in this case, a is what? Let's say 0, right? 0 plus
K.
yes, well, delta x or 3 over n. Very good. So, by the way, usually if it begins with 0, students have less problems with it, right? Because it's more compact. So this is k 3 over n. So therefore, the integral, so what we need to calculate is limit as n goes to infinity of Rn which is limit of the sum, limit of the sum of 4 plus 2 times k 3 over n times 3 over n. Okay, so first make sure that you can get it to this form. So can you see that this is the sum 4 plus 2 3 over n No squares yet. Oh, but we can make if you multiply 3 over n, sure. But I'll keep it for now like this. By the way, this is a redundant step. If you see it without doing it, then by all means. 4 plus 2 times 2, 3 over n plus 4 plus 2 n 3 over n times 3 over n. This is limit as n goes to infinity, and I can group it together, right? I can group the 4 times 3 over n together. So notice I can group 4 times 3 over n together, so that would be the summation k1 to n 4 times 3 over n plus I can factor out 2 times 2 times 2 times 3 over n times 3 over n squared. So therefore, and then times k. Just grouping together, right? Multiply it out, group together. In fact, it's easier to do it just without expanding the sum. If you just look at it, just distribute the 3 over n. So it's 4 times 3 over n plus 2 times k times 3 over n squared. If you distribute it, and then you distribute the sum.
Why is it easy to split them up?
Why do I split them up? Because I will have a closed formula separate for this part and separate for this part.
But that's going to be constant.
No, but it's going to be, you're right, it's going to be constant, but what's the constant? Do you see what it is going to be?
Infinity.
No.
Oh, it's right. Okay.
Be very careful, right? So yes, it's going to be a constant. So let's see what constant is that going to be. So what we have is this number is the same as 4 times 3 over n times what? It's 4 times 3 over n added to itself n times. So this is times n. So it's going to be just 4 times 3, or 12. Plus, if I factor out 2 and 3 over n squared, I have summation of just k. So this is 12 here, plus 2, 3 over n squared, times the summation of k, which is n plus 1 over 2. So in the limit, this is just going to be 12 plus, this is just going to be the 2 crosses out, so it's just going to be 3 squared, or 9. 12 plus 9. So 21. Okay?
What happens to n?
When I push the limit to infinity, this n squared is basically the denominator leading term well, if I cross out this 2, the denominator leading term is just n squared. Numerator leading term is 3 squared times n squared. So in the limit, the n squares cross out. Okay, so so you should also try to remember, well, those limits. It's nice to compute them fast. Let's do maybe 1 or 2 more examples. What is the area so suppose that we have an integral from -5 to 5 of root of 25 minus x squared dx. So you see, you can try Riemann sums. That's a very horrible way to approach it. How do we figure it out? B will be a very similar example. Let's say from 0 to 4 of root 4 minus x squared, let's say. So solution. Let's draw it first. So A, what we have is y, the curve that we're integrating, it's y equal to root of 25 minus x squared. That's the same as y squared equal to 25 minus x squared. So that means x squared plus y squared equals to 25. What's the shape?
Right.
No, that's not the right triangle.
Circle.
X squared plus y squared equal to 25 is the locus of point of a circle centered at the origin with radius 5. So notice what we are integrating. So this is minus 5. This is 5. And root of 25 minus x squared is just the upper part of the circle. So what's the area? You see, sometimes I just can go and use a primitive technique to guess.
Is it 1/2?
Yes, so this is 1/2 pi times 25. Or 25 over 2 pi. Because I recognize that this curve is just the upper part of the circle. What is then B? B, very similar picture, except what? Except it's from 0 to 4. And that would be quarter circle of radius, of radius what? and I made a mistake there. I meant from 0 to 2. From 0 to 2, radius is 2. So what we have is area is 1/4 pi times 2 squared, which is 4. So the area is simply pi. Okay? All right. So what we are doing next class is we are continuing with 5.2, the definite integral. If you can read ahead of time, that will be really helpful. So we have only a few lectures to get this right. All right. If you want to go, you can go. If you have questions, you can stay after class.